Here is something that might catch you off guard. The theory of relativity, the thing most people imagine as genius-level physics, impossible equations, and maybe Einstein's famous wild hair somewhere in the background, began with a question that sounds almost childlike. What would it look like if you could ride beside a beam of light? Einstein imagined this when he was still very young, long before the world knew his name. Picture it for a moment. You are running faster and faster, somehow keeping pace with a beam of light. What would you see? Would the light freeze beside you, hanging in space like a still wave? Would it look like a snapshot of an ocean wave, frozen forever in mid-motion? That sounds innocent, but to physics it was dangerous. Because everything known about light said that a frozen light wave should be impossible. Light was not supposed to stand still. It was supposed to move at one exact speed. And yet, if ordinary motion worked the way people thought it did, then chasing a beam of light should let you slow it down, maybe even catch it. That question was the seed. And to understand why it mattered so much, we have to go back before Einstein. This story does not begin with him. It begins centuries earlier, with a man standing at the edge of a new scientific world, Galileo. In the early 1600s, Galileo understood something about motion that seems simple now, but was revolutionary at the time. Imagine you are below deck on a ship. The sea is calm. The ship is moving forward smoothly, at a constant speed in a straight line. You are inside a sealed cabin with no windows. You drop a ball, and it falls straight down. You pour water into a cup, and it pours normally. You toss something to a friend, and it moves exactly as it would if the ship were resting in the harbor. Galileo's insight was this: if the motion is perfectly smooth and constant, there is no experiment you can perform inside that cabin that will tell you whether you are moving or standing still. Constant motion is invisible from the inside. You already know this feeling. On an airplane at cruising altitude, if there is no turbulence, you can walk, drink water, use your phone, or drop something into your lap. Everything behaves normally. And yet, relative to the ground, you may be moving hundreds of miles per hour. You do not feel that speed. You only feel changes in speed. Takeoff, landing, turbulence, turning. So Galileo gave physics one of its deepest ideas. Motion is relative. There is no special universal state of rest. You are only moving compared to something else. Newton later built his laws of motion on this foundation, and for more than 2 centuries, everything seemed stable. Newton's laws worked in a moving train, on a ship, on Earth, and in the sky. The universe seemed mechanical, predictable, and beautifully ordered. Then light ruined everything. In the 19th century, James Clerk Maxwell unified electricity and magnetism into one elegant theory. His equations showed that electric and magnetic field could ripple through space as waves and forward. And when Maxwell calculated the speed of those waves, he found something astonishing. The number matched the measured speed of light. Light was an electromagnetic wave. That was one of the great discoveries in science. But it came with a problem. Maxwell's equations did not say that light travels at one speed relative to the Earth, or relative to the sun, or relative to the person measuring it. They seemed to say that light travels at one fixed speed, full stop. And that did not fit with everyday motion. If you are on a train moving 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the platform sees the ball moving at 80 miles per hour. Speeds add. That is normal. That is common sense. So, if a spaceship is moving forward and shines a light ahead, should the light not move faster from the point of view of someone outside? Shouldn't the speed of the spaceship be added to the speed of light? Maxwell's equations seem to say no. The speed of light is the speed of light. Physicists did not like this. They needed a way to make sense of it. So they imagined something called the luminiferous ether. The idea was reasonable at the time. Every wave people knew needed a medium. Sound travels through air. Ocean waves travel through water. Vibrations travel through solid materials. So, if light is a wave, what is it waving through? The answer, they thought, was the ether, an invisible substance filling all of space. Light traveled through the ether the way sound travels through air. If that were true, then the ether would provide an absolute background. The Earth, moving around the sun, should be moving through this ether. And if Earth moves through the ether, we should feel an ether wind, at least through precise measurements. Light moving with the ether wind should appear a little faster. Light moving against it should appear a little slower. The difference would be tiny, but measurable. That brought physics to one of the most famous experiments ever performed, the Michelson-Morley experiment. Albert Michelson and Edward Morley built an instrument called an interferometer. It split a beam of light into two beams, sent them in different directions, bounced them off mirrors, and brought them back together. If Earth was moving through the ether, the two beams should take slightly different times to return. That difference would show up as a shift in an interference pattern. They expected to see the ether wind. They found nothing. No shift. No difference. No matter how they turned the apparatus, no matter the time of day, no matter the season, the speed of light appeared the same in every direction. It was one of the most important failures in the history of science. They went looking for something that had to be there according to the best ideas of the time, and it was not there. Physicists tried to save the ether. Hendrik Lorentz and George Fitzgerald proposed that objects moving through the ether physically shrink in the direction of motion, just enough to hide the effect. The math worked, but the explanation still depended on the ether being real. Then Einstein looked at the whole puzzle differently. What if there is no ether? What if light really does travel at the same speed for every observer? What if this is not a problem to explain away, but a law of nature? In 1905, Einstein was 26 years old, working at the Swiss Patent Office in Bern. By day, he examined inventions. In his spare time, he thought about time, light, and motion. That year, he published one of the most important papers in history on the electrodynamics of moving bodies. It began with two simple ideas. First, the laws of physics are the same in all inertial reference frames. That means if you are moving smoothly at constant speed in a straight line, the laws of physics work the same for you as they do for someone else moving smoothly in another way. This was Galileo's principle, expanded to include electricity, magnetism, and light. Second, the speed of light in a vacuum is the same for all observers, no matter how the observer or the source of light is moving. That second idea sounds impossible. If you run toward a beam of light, you still measure it moving at the same speed. If you run away from it, you still measure the same speed. If the source is moving toward you, same speed. If the source is moving away, same speed. Light does not obey the ordinary rules of adding velocities. Einstein accepted that. and then asked what must be true if it is correct. The answer was shocking. Space and time could not be what we thought they were. The first thing to fall was the idea of absolute simultaneity, the belief that if two events happen at the same time for one person, they happen at the same time for everyone. Einstein showed this with a train and two lightning strikes. Imagine you are standing on a railway platform. A very fast train passes you from left to right. At the exact moment the middle of the train lines up with you, lightning strikes both ends of the train, front and back. You are standing exactly in the middle between the strikes. Light from both strikes travels the same distance to reach you. You see both flashes at the same time. So you conclude that the strikes happen simultaneously. Now imagine a passenger sitting at the midpoint of the moving train. From your point of view, while the light from strikes travels inward, the passenger moves forward with the train. She moves toward the front strike and away from the rear strike. So the light from the front reaches her first. At first, you might say, that is only because she is moving. The strikes really happened at the same time. She just received the signals at different times. But Einstein's second postulate changes everything. The passenger has every right to consider herself at rest. In her frame, the train is still, and the platform is moving backward. She is exactly in the middle of the train. Light travels at the same speed in both directions. If the front flash reaches her first, then in her frame the front strike happened first. You say the strikes were simultaneous. She says they were not, and neither of you is wrong. This is not an illusion. It is not a trick of perception. It is the structure of reality. Simultaneity is relative. There is no universal nows spread across the universe. What counts as at the same time depends on your state of motion. And once simultaneity changes, time itself begins to change. This leads to time dilation. Imagine the simplest clock possible. Two mirrors, one above the other, with a pulse of light bouncing between them. Every round trip is one tick. If this light clock is inside the train, the passenger sees the light move straight up and down. But you, standing on the platform, see the train moving sideways. So from your point of view, the light follows a diagonal path, up and forward, then down and forward. A diagonal path is longer than a straight vertical path. But the speed of light is the same for you and for the passenger. The light cannot move faster to make up for the longer path. So if it travels a longer path at the same speed, each tick takes more time. The moving clock runs slow, not because the clock is broken, not because light clocks are special. If only the light clock slowed down while the passenger's wristwatch, heartbeat, and thoughts stayed normal, she could detect her absolute motion. That would violate the first postulate. So everything in the moving frame slows together. Her watch, her heartbeat, her chemistry, her aging, time itself dilates. At everyday speeds, this effect is tiny. In a car or airplane, it is far too small to notice. But at speeds close to light, it becomes dramatic. A person's traveling near light speed would experience much less time than someone who stayed behind. This is not science fiction. It has been measured. In 1971, Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airplanes and compared them with clocks left on the ground. The differences were tiny, measured in nanoseconds, but they matched relativity. And today, GPS depends on this. Satellites orbit Earth at high speed, and their clocks do not tick exactly like clocks on the ground. Special relativity affects them because they are moving. General relativity affects them because they are higher in Earth's gravitational field. If engineers did not correct for these effects, GPS positions would drift by kilometers each day. So relativity is not just philosophy. It is inside your phone. Time dilation also leads to the famous twin paradox. Imagine one twin stays on Earth, while the other travels to a distant star at very high speed and returns. The traveling twin will be younger when they meet again. But why? If motion is relative, couldn't the traveling twin say that Earth moved away and came back? Shouldn't the Earth twin be younger? The answer is that the situation is not symmetrical. The traveling twin has to turn around. She accelerates, changes direction, and returns. The stay-at-home twin remains in one inertial frame. That difference breaks the symmetry. The traveling twin follows a different path through space-time and experiences less time. This sounds strange, but particle experiments confirm it. Muons created high in Earth's atmosphere should decay before reaching the ground. But because they are moving so fast, their internal clocks run slow from our point of view, and many survive long enough to be detected. Time dilation is real. And if time can stretch, space can shrink. This is length contraction. An object moving relative to you is measured shorter in the direction of its motion. A spaceship that is 100 meters long in its own frame might appear 50 meters long to you if it passes at a high enough speed. The astronauts inside notice nothing unusual. Their ship feels normal, their rulers feel normal, but from your frame its length is contracted. This is not caused by a force squeezing the ship. It happens because measuring length requires deciding where both ends of an object are at the same time. And as we already saw, at the same time depends on the observer. Time dilation, length contraction, and relativity of simultaneity are not separate tricks. They are different faces of one deeper structure. That deeper structure was clarified by Hermann Minkowski, Einstein's former mathematics professor. In a lecture delivered in 1908, Minkowski presented a geometric reformulation of special relativity. He said that space by itself and time by itself were destined to fade into mere shadows, while only a union of the two would preserve an independent reality. That union is space-time. The sentence was not merely a poetic declaration. Minkowski showed how events could be represented as points in a four-dimensional geometry, with 3 coordinates for position and 1 for time. Different inertial observers used different coordinate systems related through the Lorentz transformations already central to special relativity. Minkowski was not replacing Einstein's theory with a separate physical theory. He was giving Einstein's 1905 relativity a geometric language that made its deeper structure easier to see. Einstein did not immediately embrace that formalism, but the geometric view later became indispensable when he developed general relativity. In this picture, an object does not simply exist in space. It traces a path through space-time, called a world line. An object at rest in one coordinate system still moves forward through time. A moving object traces a differently tilted path, while light follows the boundary of what can causally influence what. Different observers divide the same space-time into space and time in different ways. What one observer calls space right now, another observer assigns to a different slice. That is why measurements of simultaneity, duration, and length can change without the underlying physical events contradicting one another. Special relativity was a triumph, but it had a limitation. It dealt with constant motion. It did not fully handle acceleration. And the most important acceleration in the universe is gravity. Newton described gravity as a force acting across space. The sun pulls Earth. Earth pulls the moon. Every mass pulls every other mass. But Newton's gravity acted instantly. If the sun somehow disappeared, Newton's theory implied Earth would immediately feel the change. Einstein knew this could not be right. Nothing, not even gravity, should travel faster than light. So Einstein needed a new theory of gravity. His breakthrough began with what he later called the happiest thought of his life. Imagine a man falling from a roof. During the fall, before hitting the ground, he feels weightless. If he lets go of a ball, it floats beside him, falling at the same rate. A scale under his feet would read 0. For those few seconds, gravity disappears from his experience. Einstein realized that a person in free fall cannot tell the difference between falling in a gravitational field and floating in deep space with no gravity at all. This became the equivalence principle. Now imagine a sealed room with no windows. You feel your feet pressed against the floor. There are two possible explanations. Maybe the room is standing on Earth and gravity is pulling you down. Or maybe the room is a rocket in deep space, accelerating upward so the floor pushes into your feet. Einstein said that locally, no experiment inside the room can tell the difference. Gravity and acceleration are equivalent. That idea unlocked general relativity. If acceleration affects light, then gravity must affect light too. Picture a beam of light crossing an accelerating rocket from one side to the other. While the light travels across, the rocket moves upward. From inside the rocket, the light appears to curve downward. If acceleration and gravity are equivalent, then gravity must bend light. This was astonishing. Light has no rest mass, yet gravity should curve its path. Not because gravity pulls on light like a rope, but because gravity changes the geometry through which light travels. Einstein also realized that gravity affects time. A clock deeper in a gravitational field ticks slower than a clock higher up. Your feet, slightly closer to Earth's center than your head, age a tiny bit more slowly. The effect is incredibly small, but real. Again, GPS must account for this. Satellite clocks are higher above Earth, where gravity is weaker, so they tick faster than clocks on the ground. At the same time, they move fast, which makes them tick slower. The final correction is essential. Gravity bends light. Gravity bends time. But Einstein still needed the full mathematical theory. That took years. From 1907 to 1915, he struggled. Special relativity had come quickly by comparison. General relativity was far harder. Einstein had the physical idea, but he needed the mathematics of curved spaces. Differential geometry, tensor calculus, the work of Riemann. He turned to his old friend Marcel Grossmann, a mathematician who helped introduce him to the tools he needed. Together, they worked toward equations that could describe how spacetime curves in the presence of matter and energy. But the path was not straight. Einstein made mistakes. He published incomplete versions. He doubted the correct equations, then returned to them. By 1915, another great mind was approaching the same problem. David Hilbert, one of the greatest mathematicians of the age. Einstein and Hilbert were now moving toward the final equations almost at the same time. The pressure on Einstein was intense. This had been his vision for nearly a decade, and now someone else might finish it first. November 1915 became one of the most dramatic months in science. Einstein presented a series of papers to the Prussian Academy. Week by week, he corrected his equations, pushed closer, and finally arrived at the form we now call the Einstein field equations. During this same month, he tested his theory on a mystery that had bothered astronomers for decades: Mercury's orbit. Mercury does not orbit the Sun in a perfect repeating ellipse. The point of closest approach slowly shifts over time. Most of this shift can be explained by the gravity of other planets. But a small amount remained unexplained: 43 arcseconds per century. Newton's theory could not account for it. People had even imagined an unseen planet closer to the Sun, called Vulcan, to explain the discrepancy. But Vulcan was never found. Einstein used his theory to calculate Mercury's extra precession. The answer came out exactly right: 43 arcseconds per century. When Einstein saw the result, he knew. The theory was not just beautiful, it was touching reality. On November 25, 1915, Einstein presented the final field equations of general relativity. In simple words, the equations say this: matter and energy tell spacetime how to curve. Curved spacetime tells matter how to move. Gravity is not a force in the old Newtonian sense. Gravity is geometry. Earth orbits the Sun, not because the Sun pulls it across empty space with an invisible rope, but because the Sun curves space-time, and Earth follows the natural path through that curvature. A falling apple is not being dragged downward by a mysterious force. It is following a path through curved space-time. This was a new universe, but a theory needs tests. General relativity had already explained Mercury. But the most famous early test would come from light bending near the Sun. Einstein predicted that starlight passing close to the Sun should be deflected by the Sun's gravity. Newtonian reasoning predicted a smaller deflection. Einstein's full theory predicted twice that amount. A total solar eclipse offered the chance to test it. During an eclipse, the moon blocks the Sun, and stars near the Sun become visible. If the Sun bends their light, their apparent positions should shift slightly. In 1919, Arthur Eddington helped lead an expedition to observe a total solar eclipse. Eddington was a British astronomer and a Quaker pacifist during the aftermath of World War I. There is something deeply human about this moment. A British scientist testing the theory of a German scientist just after a devastating war, using the sky itself as the laboratory. The observations were difficult. Weather interfered. The measurements were delicate. The data was not perfect. But the results supported Einstein's prediction. In November 1919, the news exploded. Newspapers announced a revolution in science. Newton's universe had been overturned. Einstein became famous almost overnight. The public story was cleaner than the actual science. The eclipse data had large uncertainties, and later measurements were needed to confirm the result more precisely. But the direction was right. Better technology would eventually confirm Einstein's light bending with great accuracy. General relativity had passed its first great public test. And then something strange happened. For a few decades, general relativity became admired but quiet. The main action in physics moved to quantum mechanics, atoms, nuclei, and particles. General relativity was beautiful, but difficult to test and far removed from laboratory physics. Still, its equations were quietly opening doors. One of those doors led to the universe as a whole. In 1917, Einstein tried to apply his equations to cosmology. He assumed, like most people at the time, that the universe was static and eternal. But his equations did not naturally give a static universe. They suggested that the universe should expand or contract. Einstein did not like that, so he added a term to hold the universe still, the cosmological constant. Later, Alexander Friedman showed that Einstein's equations naturally allowed expanding universes. Georges Lemaitre, a Belgian priest and physicist, connected those ideas to observations and proposed that the universe had begun from a primeval state. Then, Edwin Hubble observed that distant galaxies were moving away from us, and the farther they were, the faster they receded. The universe was expanding. Einstein's static universe was gone. For a long time, he reportedly regretted adding the cosmological constant. But the story did not end there. In 1998, astronomers studying distant supernovae discovered that the expansion of the universe was not slowing down as expected. It was speeding up. The universe's expansion is accelerating. To describe this within general relativity, physicists brought back something very much like Einstein's cosmological constant. Today we call it dark energy. The term Einstein, once added to keep the universe, still returned as part of the explanation for why the universe is expanding faster and faster. That is one of the humbling patterns in science. Sometimes an idea is wrong for the reason it was invented, but right in a deeper way. Another door opened almost immediately after Einstein finished general relativity. In 1916, while serving in the German army during World War I, Karl Schwarzschild found the first exact solution to Einstein's field equations. His solution described spacetime around a spherical, non-rotating mass. It was elegant, but hidden inside it was something strange. At a certain radius, now called the Schwarzschild radius, the equations seemed to behave strangely. For the Sun, that radius is about 3 kilometers. The actual Sun is far larger, so nothing dramatic happens. But what if a mass were compressed inside its Schwarzschild radius? For decades, many physicists thought nature would prevent that. Then, in 1939, J. Robert Oppenheimer and Hartland Snyder showed that a sufficiently massive star, after exhausting its nuclear fuel, could collapse under its own gravity. If nothing stopped it, the collapse could pass the Schwarzschild radius. From outside, the star would effectively disappear. It would become a region of space-time from which nothing, not even light, could escape. A black hole. The name black hole came later, popularized by John Wheeler in 1967. Before then, people used names like frozen stars or collapsed stars. But black hole captured the idea perfectly, a place where space-time becomes a one-way door. The deeper understanding came in the 1960s, especially through Roger Penrose. Penrose showed that under very general conditions, once gravitational collapse passes a certain point, singularity formation becomes inevitable. It did not require perfect symmetry. It was not just a mathematical trick. Black holes were not an embarrassment of the equations. They were a real prediction. And then observations began to catch up. X-ray astronomy revealed strange compact objects. Cygnus X1 became one of the first serious black hole candidates. Later, evidence for black holes grew stronger and stronger. Then came one of the greatest confirmations of general relativity. In 2015, LIGO detected gravitational waves for the first time. The signal came from two black holes merging more than 1 billion light-years away. As they spiraled together, they shook space-time itself, sending ripples outward at the speed of light. By the time those ripples reached Earth, they were unimaginably faint. LIGO's detectors measured changes smaller than a fraction of a proton's width, and the waveform matched Einstein's predictions. A century after general relativity, the theory passed a test in one of the most extreme environments in the universe. Then, in 2019, the Event Horizon Telescope released the first image of a black hole's shadow. The supermassive black hole at the center of galaxy M87, a glowing ring, a dark center. Light bent around a region from which it could not escape. It looked like what the equations had predicted. Einstein had imagined light, time, and motion. His equations had led us to the edge of darkness, but general relativity, for all its success, is not complete. We know this because the universe has another great theory: quantum mechanics. General relativity describes gravity as smooth curvature of space-time. Quantum mechanics describes the small world of particles, fields, probability, and uncertainty. Both theories work incredibly well in their own domains, but when we try to combine them, the mathematics breaks. At the center of a black hole, general relativity predicts a singularity, a place where density and curvature become infinite. At the beginning of the Big Bang, the entire observable universe was compressed into an extreme state where quantum effects and gravity should both matter. In those places, our theory stops speaking clearly. This is the search for quantum gravity. String theory is one attempt. Loop quantum gravity is another. There are other ideas too, but no final theory has been confirmed. And black holes sharpen the problem even more through something called the black hole information paradox. In the 1970s, Stephen Hawking discovered that black holes are not entirely black. When quantum theory is applied near the event horizon, black holes should emit faint radiation. Over unimaginably long times, they can slowly evaporate. This is Hawking radiation. The idea is subtle, but the basic picture is this: empty space is not truly empty. Quantum fields fluctuate. Near the event horizon, those fluctuations can result in particles escaping, while the black hole loses a tiny amount of energy. For large black holes, this radiation is extremely weak. A black hole with the mass of the Sun would take far longer, far more than the current age of the universe to evaporate. But in principle, if enough time passed, the black hole could disappear. And that creates a problem. Imagine throwing a book into a black hole. The book contains information, words, ink patterns, molecular arrangements, quantum states. In classical general relativity, that information crosses the horizon and is hidden from the outside. But if the black hole eventually evaporates into Hawking radiation, what happens to the information? The radiation appears thermal and random. It does not obviously carry the details of what fell in. The book is gone. The black hole is gone. The radiation seems to contain no record of the book. That would mean information has been destroyed. Quantum mechanics says that cannot happen. Information can be scrambled, hidden, spread out, made practically impossible to recover, but not fundamentally destroyed. So, black holes place general relativity and quantum mechanics in direct conflict. Hawking originally argued that information really was lost. Later, he conceded that information is probably preserved somehow. But exactly how remains one of the deepest questions in physics. One powerful idea is that information may be encoded on the event horizon itself, like a hologram. This connects to the holographic principle, the possibility that information inside a volume of space may be described by information on its boundary. That sounds almost unreal, but it grows naturally from black hole physics. Black hole entropy seems to depend on surface area, not volume. That suggests that the boundary of a region may contain deeper information than we once imagined. If this idea extends beyond black holes, it may tell us something profound about reality itself. Maybe space is not fundamental in the way we think. Maybe space-time emerges from something deeper. Maybe geometry, gravity, and information are all connected. This is the frontier. And now, stepping back, the arc of the story becomes almost breathtaking. We began with Galileo's ship, the simple idea that smooth motion cannot be detected from inside. Then Maxwell discovered that light has a fixed speed hidden in the laws of electromagnetism. Michelson and Morley searched for the ether and found nothing. Lorentz and Fitzgerald tried to save the old picture. Then Einstein accepted the impossible. Light speed is the same for everyone. From that came a new understanding of time. There is no universal now. Moving clocks run slow. Moving lengths contract. Space and time are woven together into space-time. Then Einstein went further. He realized that gravity and acceleration are deeply connected. A falling person feels weightless. A rocket accelerating upward feels like gravity. Light bends in a gravitational field. Clocks tick differently depending on gravity. After years of struggle, he wrote equations showing that gravity is not a force pulling through space, but the curvature of space-time itself. Those equations explained Mercury's orbit. They predicted the bending of starlight. They revealed an expanding universe. They allowed the cosmological constant and later dark energy. They pointed toward black holes, gravitational waves, and the deep connection between gravity and information. Every time we built better instruments, we tested the theory again, and again it held. But the story is not finished. Newton's gravity was not thrown away when Einstein came along. It became part of a deeper theory. It still works beautifully in the right domain. Einstein's gravity may someday be treated the same way, not wrong, but incomplete, a special case of something deeper. That is how science grows. Understanding does not simply replace itself. It accumulates. One layer becomes the foundation for the next. Einstein built on Galileo, Maxwell, Lorentz, and Minkowski. Penrose, Hawking, Wheeler, and others built on Einstein. And someday, someone will build the next layer. A theory that joins quantum mechanics and gravity, explains black holes completely, and shows us what space-time really is. Maybe that theory will come from an equation. Maybe from an experiment. Maybe from another simple question, the kind a teenager could ask. What would it be like to ride beside a beam of light? That question opened a door. And through that door came a universe where time can slow, space can bend, gravity can curve light, black holes can trap stars, and the edge of a shadow can teach us something about the nature of reality itself. There is another reason relativity matters so deeply. It did not stay locked inside chalkboards. After Einstein, physicists kept looking for ways to catch space-time in the act. Some tests were quiet and precise. Some were cosmic and violent. Each one asked the same basic question in a different language. Does nature really behave as the theory says? One of the most elegant confirmations came from clocks. If gravity changes time, then a clock at a higher altitude should tick at a slightly different rate from one lower down. The effect is tiny, but modern atomic clocks can see it. Move a clock upward, even by a modest amount, and the difference becomes measurable. The old human feeling that time is the same everywhere turns out to be only an approximation that works because our lives are small compared with planets and stars. Another confirmation came from binary pulsars. A pulsar is the dense rotating remnant of a dead star, sending beams of radiation across space like a lighthouse. When two compact stars orbit each other, general relativity predicts that they should lose energy by emitting gravitational waves. Long before LIGO directly detected those waves, astronomers watched a binary pulsar slowly change its orbit in exactly the way relativity predicted. It was as if the system were whispering the truth of gravitational waves, decades before human instruments could hear them directly. There were also tests of frame dragging. In general relativity, a rotating mass does not merely sit inside space-time. It slightly drags space-time around with it. Earth does this very weakly. A spinning black hole does it powerfully. Near such an object, space and time are not just curved, they are twisted. Orbits, light paths, and the behavior of matter in an accretion disk all carry signs of that rotation. This is one of the strange features of relativity. Gravity is not simply down. Around massive objects, gravity becomes a landscape. Around rotating objects, that landscape has a current. Matter can swirl, light can loop, and time can behave differently from one path to another. Relativity also became one of astronomy's greatest tools through gravitational lensing. A massive galaxy or cluster of galaxies can bend the light from objects behind it, stretching distant galaxies into arcs or even producing multiple images of the same object. At first, this sounds like a distortion, as if gravity is confusing the view. But the distortion is information. By studying how light is bent, astronomers can map mass, including mass that does not shine. In that sense, relativity helped reveal the invisible architecture of the universe. It gave scientists a way to weigh clusters of galaxies, study dark matter, and see objects whose light had been magnified by the curvature of space-time itself. Black holes made the theory even more dramatic. A black hole is not simply an object with strong gravity. It is a region where the geometry of space-time creates a boundary, the event horizon. Outside it, paths can still lead away. Inside it, every future-directed path leads deeper inward. The horizon is not a solid surface. You would not strike it like a wall, but it is a real causal boundary, a place after which return is impossible. For someone far away, matter falling toward a black hole appears to slow and fade as its light is stretched to longer wavelengths. For the falling object itself, nothing special may happen at the horizon of a large black hole. This difference in description feels paradoxical, but it is relativity doing what it always does, showing that time and observation depend on the path taken through space-time. Near black holes, ordinary intuition becomes unreliable. A stable circular orbit may not exist if you get too close. Light can orbit briefly before escaping or falling in. Energy can be extracted from rotating black holes under the right conditions. Jets can shoot from the regions around supermassive black holes, not from inside the horizon, but from the extreme magnetic and gravitational environment around them. And yet, even in these wild places, general relativity remains astonishingly calm. The same theory that corrects satellite clocks also describes the collision of black holes. The same geometric idea that explains Mercury's orbit also shapes the image of a glowing ring around darkness. That unity is part of the beauty. A good theory does not merely explain one thing, it connects things that once seemed unrelated. A falling apple, a bending beam of starlight, a clock on a satellite, a dying star, a galaxy cluster, and ripples from merging black holes all become chapters of the same story. Still, relativity also teaches humility. It shows that common sense is local. Our intuition was formed at slow speeds, weak gravity, and small scales. We evolved in a world where light seems instantaneous, clocks seem universal, and the ground seems still. That world is real, but it is not the whole world. It is one gentle corner of a much larger structure. The deeper universe is stranger. Time is not a single river flowing identically everywhere. Space is not a passive stage. Gravity is not an invisible string pulling across emptiness. The universe is a woven geometry of events, paths, horizons, and limits. And at the edge of that geometry, where quantum mechanics and gravity meet, the story waits unfinished. So let the equations fade for a moment. Let the names and dates soften into the background. Galileo's ship, Maxwell's light, Einstein's train, the falling man, Mercury's orbit, Eddington's eclipse, Schwarzschild's radius, Penrose's collapse, Hawking's radiation, LIGO's whisper from distant black holes, the glowing ring around M87. All of it belongs to one story, a story about motion, a story about time, a story about gravity, and maybe, beneath all of that, a story about information, about what the universe remembers, what it hides, and what it never truly loses. There is also a softer human side to this story. Relativity changed physics, but it also changed the emotional shape of the universe. Before Einstein, many people imagined reality as a single great clockwork mechanism, ticking the same way everywhere. There was comfort in that image. One space, one time, one cosmic stage, everything moving inside it. Relativity removed that simplicity. It told us that observers carry their own measurements of time and distance. It told us that two people can disagree about the order of distant events and both be following the laws of nature. It told us that the universe does not care whether its deepest rules feel intuitive to creatures who evolved on one small planet. And yet it did not make reality chaotic. It made reality more precise. There is still order. It is just a deeper order than the one our senses first suggested. Beneath the shifting measurements, space-time has structure. Light cones define what can influence what. Proper time measures the path a traveler actually experiences. The speed of light creates a cosmic limit, not because engines are weak, but because causality itself seems built around it. This matters when we imagine the future. Interstellar travel, if it ever happens, will not be ordinary travel with larger engines. Relativity says that distance, time, energy, and communication all become profound obstacles. A crew traveling near light speed might experience less time than Earth, but Earth would still change while they were gone. Messages could not travel instantly. A human civilization spread across stars would never share one universal present. The old dream of space as an empty ocean is incomplete. Space has rules, distance has consequences, time has texture. Even so, relativity does not close the universe. It teaches us how to move through it honestly. It tells engineers how to correct clocks, astronomers how to read bent light, and physicists how to listen for waves in spacetime. It tells dreamers that the stars are far, but it also gives them the true map. And maybe that is why the theory still feels beautiful. It takes away an easy universe and gives back a real one. The universe is under no obligation to be understandable. And yet, somehow, it is, at least enough for us to follow the light.